I'm the chairman of this session. My name is Haibang Zhang from National Taiwan Ocean University. Each jury, please introduce yourself. Mr. Lee, please.
Okay. Guolong from Taiwan.
I'm Minkai Li from National Central University.
Junong from Zhongzhen University.
Guolong from Dongma Dashi.
Okay. So reporter, please introduce yourself.
Hello everyone, we are from Jijin High School and we are in OC and I'm Chen Dingxiang. I'm watching his detail and he is Wang Ziji.
Okay, thank you. Opponent, please introduce yourself and the members.
Greetings everyone, I'm the captain Xu Yilun from television and my teammates Huang Xuelan, Han Weiming, Chen Bingyun, Zheng Youyun.
Okay, thank you. And the reviewer, please introduce yourself and the members of the team.
Tim Tesla from Central High School. And this is Jin Sang, 国军国贸武汉我是右西，谢谢。
Okay. And the opponent who can begin to challenge the problem to the reporter. You have 1 minute.
The one to challenge problem number 3, bring on the right.
Okay, number 3.
Challenge accepted.
Accepted. Yeah. Please also, each team please write down the presenter name on the board. Reporter, you have 5 minutes for your preparation. So we're making a report now. Okay. So please take the floor. You have 12 minutes.
Honorable judges and fellow competitors, today I'm going to report my topic number 3, ring on the rod, and I'm from Team 40. So here's the problem statement. A washer on a vertical steel rod may start spinning instead of simply sliding down. Study the motion of the washer and investigate what determines the terminal velocity. So according to the problem statement, we have two main focus. First one is to find the frequency and then calculate the terminal velocity. And the second main focus will be in what conditions will affect the terminal velocity. And here's our outline. We will first discuss our observation and theory, experimental setup, variables, data analysis, and conclusion. So here's the observation. So we can see that when the ring goes down, it will first free fall for a distance and then it starts to spin in a more stable way. So this is what we are going to talk more deeper into. So here's our theory. So our theory is like the normal force will equal to mr omega squared, and then the force the picture in the left can describe how the equation works. So we ensure that we want to see the falling with a constant velocity. So the friction will be like this, and then if we do some simple calculation, we can find out that the omega squared will be g over mu k times r times sin theta. And in this equation, we can find out that the mass won't really affect our results. So here's our experimental setup. So we decided to use 4 different types of rings, and the first one and the second one would be the inside diameter is 4 centimeters and the outside diameter is 6 centimeters, but in different mass. So the second one is we have the first one taped in 2, so there's a different mass. And the third one and the fourth one will be the inside diameter is 2 centimeters and outside diameter is 6 centimeters, but in different mass, just like the previous one. And the picture in the right will be the demonstration of how we are going to record this experiment. So we have a phone on the top of it to record how it's being, and one on the side to record how it goes down. So here are our variables. So we decided to control our jumping distance, so like we only want to do different variables on the rings, so instead of the rod. So we control the jumping distance in 1.17 meters, and also we control the initial omegas to let the rings are to be more stable. And the independent variables we are going to do is the difference of the inside diameters and outside diameters, which is 4 and 2. And then we decided to do the release angle in 0 degrees, which is parallel to the 4, and 15 degrees and 30 degrees. And that's, although the math won't really affect the results according to our theory, but we decided to do the experiment to prove it. And that's the dependent variables which we are looking forward to is the frequency and then the terminal velocity. So here's our first data analysis. So the relationship between inside radius and frequency. So according to the picture in the left, it has the inside centimeters of 2, and the right it has the inside centimeters of 4. So obviously you can see that the frequency in the right will be way higher than the left one. So we can have the results that if the inside radius is bigger, it will have a higher frequency. So if we did the frequency and make it into a VP chart, we can see that the relationship between dropping speed and its inside diameter. So according to these two charts, we can see that it drops in a constant velocity, which we want to make sure that it drops in constant velocity. So it matches with our theory. And you can see that although there are very similar, but the chart in the right, you can see that the velocity is bigger than the left one, and yeah. So the third data analysis is the relationship between the angle when it was released and its dropping speed. So according to the data, we decided to choose the ring which has the outside diameter 6 centimeters and inside diameter 4 centimeters, and with only one pieces of ring which has the very least mass. And we decided to do it in 3 angles, which is 0 degrees, 15 degrees, and 30 degrees. So the angle will be like the rod is like this, and if the 0 angle is like this, so we decided to choose 0 angles, 15 angles, and 30 angles like this. So according to the chart, we can see that when it was released in the 0 angles, it had the data of just like the previous chart. So it will drop constantly in velocity. But when we release the angle in 15 degrees, you can see that here's the speed in the very first part. It wasn't really a constantly falling velocity. You will first free fall for a distance, and then you will go through a critical point, and then it will be more stabilized. So in this picture, you can see that the point over there, the critical point, will be a little bit lower than 0.8 centimeters over second, so it might be our terminal velocity. And this one will be the angle when it was released in 30 degrees. So you can see that here it comes from a little bit more than 1.1 to 0.6. So we can see that the free fall distance increases when the angle increases, and the terminal velocity over here of the critical point will be a little bit higher in 0.6 centimeters over second. So we can have a conclusion to that. When the angles increase, the terminal velocity will decrease. So here's the fourth data analysis, the relationship between the mass and frequency. So it is released in the 0 degree, which is parallel to the flow. So according to our data, we can see that the right side is the ring which we tape it into 2, and the left side is only 1 ring. So you can see the frequency is, although it didn't really has a very different observation, but if we actually counted how many times it turns, we can see that the right side has a little bit much bigger frequency than the left side. So the very different part of these two charts is the range of its frequency. So the only one ring that goes down has a smaller range of the frequency, moving upward and downward, but in the second chart, the range of the moving frequency goes much more higher and much more lower. So the fifth data analyzed will be the relationship between dropping speed and its mass. So according to our theory and our previous data, we can see that if we release in the 0 degrees, which is parallel to a pole, the velocity will be constant, and it falls in constantly velocity. And both two pictures might have the same result as we wanted. But over here, the right side of the ray line, the speed actually just fall down and it became a free fall body because what we saw is that the mass is too big and it used too much energy to spin. So when at last the angular velocity is not big enough to let the friction hold on the ring to rotate. So here's our final conclusion. If the inside radius is bigger and with enough speed, it will have a higher frequency and higher velocity, but it won't actually affect our terminal velocity. And then the second one, when we release the ring with an angle, it will first free fall for a distance until it is balanced. So like just what I said. So the third one is when the angle increases, the free fall distance will increase, but the terminal velocity will decrease. Like when we turn to 30 degrees, the free fall distance will increase, and then the terminal velocity will be smaller than the one releasing 50 degrees. And the fourth one is when the mass change, the ring still falls in constant velocity, so it matches with our theory because the mass won't really affect the result. And the last one, when the mass is too big, the angular velocity will decrease faster, and indeed the friction will decrease faster too. So at last, it won't have enough friction to let the ring rotate on the rod. And thank you everyone.
Okay. Now, the opponent, you have 2 minutes for the you can ask question to the reporter.
Please turn to page 7. Have you ever tried release with omega mass equal to 0? Just that is a free fall.
No. So but it won't spin. So like you just like put it over there, it will just fall down.
Okay. Have you ever tried the roof rod?
No. That is a controversial.
And turn to the theory. Oh yes. This means in the beginning they arrive the terminal velocity.
No, it will free fall for a distance and then it arrive at the terminal velocity.
And what you say the falling with constant velocity and this formula is means the whole motion is fit with this formula.
Now we are looking for the critical point when it goes to the terminal velocity.
Turn to page 9. Is why the frequency higher the angle, why the angle bigger the terminal velocity and less.
So it's not this page.
Oh, I'm sorry.
So you want to see here. So when the angle increases, it will free fall for distance, and then the balance speed will be slower, in which we use tracker to track it, and it was just like this.
Time is up.
No.
So the opponent has 3 minutes for the preparation. Okay, opponent, please take the floor.
Hello everyone, I'm Iris Shade of Vision from John Hartville Senior High School. And let me give the permit-driven rock. And this is our permit statement, and we started the motion of the water and what determines the terminal velocity. And overview the observation is video and start up and arrive terminal velocity in the end. And their experiment is made of brief and difference in the inside and outside diameter and the previous angle. And the analysis is the frequency and the terminal velocity and the relationship between the drawing speed and its base. And this one. In conclusion, the motion of the water is release ring with the angle and because of the balance and the bigger the velocity, the bigger frequency gets. The demonstrate the ring flows in the constant velocity. The advantage is a redundant experiment abandoned the result that in investigation stick to problem statements and assertion as a non-theoretical experimental quantitative analysis and quantitative analysis and lack quantitative analysis and lack of parameter conducted and the division between theory and experiment data not will explain. And I want to discuss the motion of the water and it may conclude a slide up and down and then will arrive the terminal velocity is in the end. I want to discuss why a reason and friction toward air resistance affect the terminal velocity, and we also have the angle of insulation. And when we say the water top view, it may have revolution and speed. And when we discuss the whole motion, it may have a precision and an angular momentum. And the parameter I want to discuss is the roughness and depth and non-depth of the rod and width of the rod and weight of the water and the initial angular velocity. And theory, I want to discuss the torque formula and the centripetal force multiplied by mu k and equal to Fk equal to mg. And I want to discuss how this formula influence the experiment in the end. And in conclusion, I want to study the torque make the warp spin and slide down in warp pi and the rotation and revolution of the water and the relationship between radius and the speed of spin. And about the analysis, I want to know how you calculate in the page 3. You say you have the friction. I want to know how you calculate friction. And when they have an angle, and how can you to study the whole motion or the force diagram. And they also have collision. So I want to know if the energy and the energy loss, if the collision affects, and this formula and why that arrive the terminal velocity. And this is about the when the meteor and arrive terminal velocity in the air. But we can use this formula to explain the whole motion of the water and the rod.
Okay. We will continue discussion with the reporter.
I want to discuss. I want to ask you. Have you discussed the top view? As you said, you have top view, and have you find some interesting thing when you see on the top view about the water speed and revolution?
So going to our top view of our recording, actually we can't see anything after it spins for like 2 to 3 seconds because the wind is not big enough to let the phone to record.
So do you see the water speed rotate around the central place? Do you catch the moments?
I catch the moment, but it wasn't the whole process. It only kept the first 2 or 3 seconds because the rod will actually hide the.
But the question says that we need to study the motion.
So we decided to use from the side.
Oh, so your important is as the side view.
Yeah.
So please turn to the why water arrives at terminal velocity.
So
Can you explain?
So the water arrived to terminal velocity because of the friction. So when we
Because
release
in this slide, it ignores the initial condition in the initial rod initial condition. If you ignore it,
so we want to control it at the control variables because it's very hard to control the initial omega. So we decided to only calculate the critical point, so it will go to the terminal velocity and then it will stabilize after it goes to the critical point.
do you think that because you release the water in a 0 meter per second, and they faster and faster, but they will be a trend like I think in the cycle. It's a big diagram. In the cycle, we release the water in a 0 meter per second, and they will, because of gravitation, will be faster and faster. And because of friction or some force, there will be a smooth line. And this line is called terminal velocity.
So actually we do not see that thing because according to our data, we found that when we use the tracker to check every point of the tape we use on the ring, and then we use tracker to track its trace, and then we found out we would drop in constantly velocity.
So you don't ignore this.
We didn't solve the thing before.
Okay. And I want to ask, the rod will spin itself?
What the rod? No.
Oh, okay. And I want to ask, can you explain the omega will have unstable line?
What do you mean by that?
Can you change your slide? define the range what will they have frequent acceleration.
So what we think is like maybe the inside diameter is not big enough to let the wings to go have a very enough place to let it move. So
Can
we
you
have
draw
a,
the force diagram?
So no, the fourth diagram is just like this. Just like yeah. It's just like this. So we only consider there's one connect point on the rim to the rod. So
Wait, so the picture is the side view?
yeah, this is like
It's the side view?
yeah.
And how they have the terminal velocity. And in this picture, it didn't have terminal velocity.
So I'm just talking about frequency, and then I will go on to the next page to talk about the terminal velocity. So this is what I see in my experiment. Because the inside diameter is not big enough to let it go up and down, so it will go up and down very fast, so the frequency will go faster than the left one.
Also, it can show the diagram that around the velocity.
So do you want to do this one? This one?
But this velocity can be changed. Terminal velocity means it has a smooth line.
Yeah, so we didn't see terminal velocity in this one, so this.
So in the whole motion, you didn't see the terminal velocity.
Yeah. When we change the release angle, we see the terminal velocity, so it might be the major parameters of our experience.
And in my opinion, I think the friction during the time, the friction will receive the gravitation, so they have a terminal velocity. Oh, sorry, I don't want to draw the first diagram. And I want to ask, have you ever tried, you have 0 omega naught and try, yes, 0 omega naught. Initial angular velocity is 0, and you just like that.
So like maybe we have a different experimental setup, so our rod is like very smooth, so when we release in the 0, like you just see then it will fall down like
So
itself.
have you ever tried the roof rod?
So we didn't actually change our rod.
In my opinion, when we release the washer in a zero initial velocity, and when it spirals down on a roof rod, and roof rod has a texture, and the washer will have almost the same motion and have terminal velocity.
So actually we didn't do that, so maybe we can improve in our future.
And why do you think in this picture you don't have the terminal velocity? What happened to you?
In this picture, there's terminal velocity. So in this point is the critical point is the terminal velocity.
Why they had you can predict it? You can guess what condition make it no terminal velocity. Okay.
So in this, we only use 3 different parameters, which is the mass and this angle and the first one. So when we actually did our experiment and used the tracker to check the tracing, we found out that the only really major parameters that may affect the terminal velocity will be the angle release. So yeah.
Have you ever seen that you change the washer? I can see what is the weight of the washer? Wait. It's only had okay. Have you ever tried the more heavier? Just or like
So
with
yeah,
steel or some just like this one.
We didn't actually try the steel one, but indeed we have the one that I use with PF3 rings together, but the mass is too big enough so that it can really spin very long. It cannot really last very long, so we cannot actually test the trees.
I think you don't have the terminal velocity maybe because of the friction or the mass. the A maze and it's for the centripetal force because the centripetal force because the normal force and normal force can cause the friction. So I think it makes the problem you can get the terminal loss. It's fine. You can try it at your home. And in the fourth diagram, yes, the fourth diagram. Have you considered the air resistance is the factor that causes the terminal velocity?
Yes, we did. We want to. So our theory is like it will fall down in a constantly velocity. So if we include also resistance, it will just be like this. And actually, that is something that we can actually control. So we didn't actually do that.
Okay, time is up. The Bowman, you have 1 minute to summarize the discussion.
With the top, maybe the friction and the torque can get the terminal velocity, and the reason why they can't get their terminal velocity maybe because of mass, the centrifugal force, and some other force. And I want to and discuss that he didn't investigate the top view, and I think it may be a reason that can get terminal velocity and some interesting motion. So I think it's a very necessary. And we also discussed we made the right terminal velocity when we use the rough rod, and we don't need to give it initial angular velocity.
Okay, time is up.
Thank you.
So review. Please ask questions to the reporter and opponent. You have 3 minutes.
Okay, and in this and I want to ask the reporter, how do you do the move of the rod? Because when the ring, because yes, the rod, because when the ring is spinning on the rod will move.
So actually, we take it on the floor and on the top of our setup, so it won't actually spin or move.
Okay, and what how do you use the constant velocity?
So according to our chart and the tracker, we try to trace, and if actually goes out, it will become the constant velocity.
But the constant velocity also, every experiment you do it once and you will have a different constant velocity.
No. So the picture you saw was the average of we did like more than 30 times, and we have the more than 10 grams and 10 charts. So we actually put it together to find the best line of the constant velocity.
Okay, and I want to ask is what's the parameter you think can cause the ring and the different?
Maybe it's the omega or the force of the texture, or the weight of the rod,
And the function you even the things doesn't give any translate for the terminal velocity. Or your function for terminal velocity.
My function for terminal velocity is mg equal to kg squared, and in we can see we can understand that when friction balanced by the rotation, and then we'll get the terminal velocity, and when the terminal velocity is related to the itself the velocity.
Okay. And so if your every of the experiments can lead to the daily content, or if not, then possible.
So if we have the mass that won't go too far, so we can go stabilize it at the end.
And because sometimes we can.
The mass is
Sorry, time is up. So review, you have 2 minutes to prepare the presentation. 2 minutes. So review, please take the floor. You have 4 minutes.
Okay, hello everyone, and I'm from Team Tesla, and I'm the reviewer. So this is a problem statement, and I won't repeat it again. And this is the performance of the reporter. Gross theoretical model where literature use clear vibrato for experiment setup, sufficient investigation of velocity to time, use accurate exchange for theory proving, clear experimental graphs, answer the questioning of method fluid theory. And but their cons is lack of experimental data, no explanation of spinning during reports, fail to build link between theory and experiment, and mention a lot about the theories but not exactly how you calculate, lack of parameters considered, and lack of measurement methods. And this is the performance of opponents. Pros sufficiently ask about key method and address some relevant topics. Summarize the report well. And for the cons is talk too much about the relative point of view, not exactly about the sound amplitude and frequency. Only focused on their own opinion instead of reviewers. And no prioritization. Okay, and also next page, and their discussion topic is what thing does the reporter saw from the top view, and the reporter considers side view is more appropriate, but we think that it should do both at a time because it's both important. And the opponent, the discussion is initial condition of the theory ignored, is their own. Oh, okay, and so the reporter said control initial omega is hard, so choose alternatives. And so, and we think that they should focus on a comprehensive phenomenon more. And then the opponent say explain the situation of graph and ask the reporter to draw force diagram. And questioning the existence of terminal velocity in a certain graph. And the reporter say terminal velocity is shown in next graph. Reviewer also we think that opponent has to comprehensive overview the report. And they also say that the opponent also question the view of terminal velocity from the reporter. And the reporter answer to the other side's equivalently important. But so I agree with the reporter. And opponent has suggested the reporter to consider the phenomena on washer. And reporter answered the experiment with composing parameters. And we think more parameters can be considered, since the experiment can be easily influenced by many other forces. Okay, and this is the end.
Okay. So, reporter, please present your concluding remarks. You have 2 minutes.
So here's our concluding remarks. We use this smooth rod, not a round rod, so we need to spin it while doing the experiment. And then we control the initial conditions to make sure how it falls down into the terminal velocity. And the major parameter to affect the terminal velocity is what we just said, the angle released. And if the mass of the ring is too large, the phenomenon will become harder to observe because the energy release will be too fast, so we cannot actually see the whole process of the ring falling down. And our data have been analyzed in the average of a lot of times. So the chart you see is the average of our experiments. And as I want to say that as our chart is actually in XC chart, when we are moving the chart from Excel to PowerPoint, we actually accidentally make the charting to the PT chart, and so sorry for the mistakes. And you can also be successful to show terminal velocity we got. Yeah, that's all.
Okay. So it's time for the question from the jury. Any question from the jury? Please, there's any, please.
Please turn to your data analysis 3. So these are XT diagram, not VT diagram.
Yeah. So we made it wrong because when we are changing into the PowerPoint, the y side is actually missing, so we just type it wrong.
So how do you know the terminal velocity has reached?
So when the terminal velocity reaches it will go constantly, and before it got more stabilized, it will free fall for distance. It won't really speak in the very first distance. So when the ring starting to spin, we can see that as the terminal velocity.
So can you point out at which time, at what time the terminal velocity is reached?
Yes, here.
And how about?
So here. So because it's in average, so we didn't actually have the exact numbers of the time and the place it was in the terminal velocity. So it's just a chart to let you see there's a terminal velocity and the relationship between the angles.
Okay, could you, would all three of you answer the same question? First, I would like the reporter to answer. What is the meaning of the slope?
This one?
No.
This one?
You have three diagrams, right?
Yeah.
You see the dropping tendency of the position, right, along the time, and for each curve or line, there is a slope, the tendency of the dropping.
Yeah.
What is the meaning of the slope? So, see first.
So actually, that isn't really a slope. It's just the point where it falls down. So like in the start is at the moment it goes from.
No. Just answer me. Why is the meaning of the slope in the XT diagram? Okay. And how about you, the reviewer? What is the meaning of the slope?
Also, if there is just a line on the XT, and so it means that it is the same velocity.
Same velocity. How about you?
It is an ST diagram, and this slope is meaning the free fall. And you can see it's a curve. It means it's faster and faster, so it's a free fall. I think it's a free fall.
What? Frequency.
Free
What is that?
Oh no, I say they will be faster and faster, and because it's a curve,
So,
it's a free fall.
oh, free fall.
But I don't know
okay.
if its
So-
direction is.
So how about the since the sign of the slope is negative, right?
Yeah.
What does that mean?
So actually, it was the. So when we are making it, we actually put it in the top. So when it falls down, it or goes down. Like when the length of the rods will be 1.17 centimeters. So actually, here is 1.17 meters, and actually we made it accordingly from the top to the bottom. So the dot will be like going negative.
Okay. And how about in the center diagram?
Yeah. This one.
Yes. Do you think that the slope is constant?
So actually, if you see only the part of the data, it won't really be constant. But actually, if you see as the whole process, the whole program, it will be actually really close to constant, and it can be considered as a constant.
Okay. So, is it any question for no? So it's time for the scoring for the jury. Okay. So let's show the score for the reporter. 5, 4, 6, 5, and 6. Okay, can we show the score for the opponent? Seven, 6, 5, 6, and 7. Now we show the score for the review. 6, 5, 5, 5, and 7. So, any question, any comment from the jury? So, no comment, and we cross this 5 here, and we have 10 minutes break. So please, sooner you can change problem to the reporter. You have 1 minute.
Okay. We want to challenge question number 4.
Number 4.
Yes.
Accept. Okay. So each team please write down the presenter's name on the board.按照顺序。 So reporter, please take the floor. You have 12 minutes.
Greeting everyone, I'm reporter Huang Shuan from TV. This is my presentation on problem number 4 on single disk. In its part segment, a metal disk with a hole at center sinks in a container filled with water, and where a vertical water jet hits the center of the disk, it may float on the water surface and explain the phenomena. And when many flows on the pressures above and below this, and the height created by the hydraulic drum, and underwater vortex caused by Bernoulli's principle. And it's our outline. The first is experimental observation, and the analysis and discussion, and final is the brief conclusion. And it's our experiment setup, and our setup conclude the nozzle and a disk with a hole at center, and a glass is round container full of water. So the higher the water hits the disk won't change. And when put the nozzle close to the disk, so we can prevent the turbulence. And we change the hole diameter and the outer diameter, control the different weight and the sand thickness, and the material we use is aluminum, and the density is less in the water. And we will analyze the top view, the side view, and underwater view motion. And it's our demonstration. And this is our demonstration video. And on the demonstration video, we can observe the hydraulic drum and the vortex. And the hydraulic drum will alter when the water jet size is larger than hole size. And the vortex will alter when the water jet flush into the water. And it's our experimentation of the hydraulic drum. On video, we can see the hydraulic drum is formed at the edge of the disk. And a water level difference H will provide upward pressure to the disk. And there are
他这个先 stop time。
行，时间可以了。
上面。
现在不
可以了。
可以了。OK。
好。
please. Okay. Okay, please go ahead.
And there are 5 forces acting on the disk. And the downward forces are from gravity and air pressure and the impact from the water jet. And the outward forces are the pressure lifted to the hydraulic drum and upward flow caused by the underwater vortex. And when the flow forces are equilibrium, the disk will remain floating. And the series of random numbers and the computer random numbers of the two water jet will use up about 10 to the power of 5, so both are nominal flow. And on the figure we can see the stream velocity decrease when the when spreading over the disk. And the first reason is shear stress. And the mu is the viscosity coefficient. And the shear stress is proportional to the velocity gradient. And because the water situation is laminar flow above mentioned, so this formula can be used. And the second reason is continuity equation. And the A1 is the surface area of the water, and the V1 is the velocity of the water. So when A1 and V1 are constant, the A2 smaller than V2. And this is a serial hydrogen. And I'm going to explain the hydraulic drum formula. So when take the speed before and after hydraulic drum, and it can be expressed in the form of F1 minus F2, and F1 and F2 is the force on water before and after hydraulic drum, and Q is the volume of water flow per second, and it can be expressed the average pressure multiply the cross-sectional area, and we can get the magnitude equation, and we plus the continuity equation and the energy equation, and we can get the equation. And we can get the equation, and when we solve the equation, we can get the y2 over y1, and we can get the formula to calculate h. And the flow number is proportional to a flow rate, and because the y2 over y1 is function to the flow number, and combine the formula we know, we can calculate, and we can know when the flow number is less than 1, no hydraulic drum will occur when the flow is less than 1. So when flow is less than 1 is in supercritical, and when the flow number is smaller than 1 is subcritical, which occur after hydraulic drum. And the hydraulic drum will try to move from the edge to the center of the disk, but the drum will be carried to the edge of the disk because of the motion of the stream, which spreads all direction from the disk, from the center. And the hydraulic drum will occur when the speed of stream is equal to the speed of hydraulic drum to the center of the disk. And this is a demonstration of vortex. Due to the viscosity, the water jet slows down after it goes through the hole. So, according to the Brownian principle, a pressure gradient is built up to set up the underwater vortex. However, the force caused by the vortex is different to measure. It's difficult to measure, but can be calculated from the equilibrium condition. With the result of gravity, the air pressure, and force from hydraulic drum, the vortex force are calculated for 2J flow rate. Higher J flow rate provide large vortex force for increase faster flow in the vortex. And for the graph, we can know when the velocity of water is larger and the diameter of hydraulic drum is larger too. And it can be explained by the formula. When the velocity of water is larger, the flow number is larger too. And when the flow number is larger, we can get a larger hydraulic drum dynamic. And the greater of the velocity of the water, the greater the flow number, and higher the hydraulic drum forms. Then it can be a full heavier disk. And according to the theory, hydraulic drum can be created as the flow number is greater than 1. This is the result of J speed threshold to create the drum. And when the hole is larger than the J cross section, no J impact in hydraulic drum. only gravity and vortex are involved. The disk still unsinkable as long as the J flow is large enough, since the vortex force is proportional to the disk area. Disks of the same size with larger hole then is larger need higher J flow to flow than the disk with a smaller hole. And this is our conclusion. The hydrodrome and underwater vortex are the reason of keep the disk unsinkable. And hydrodrome is created when first the water jet cross section is larger than the hole, and second, the J speed depends flow number is greater than 1, and third, higher J speed gives larger drum diameter and height. And the vortex is caused by the Boltzmann principle, and effective area of this is larger and the vortex force is larger. And thank you for your listening.
Okay, thank you. So the opponent, you can ask question to the reporter. 2 minutes.
Okay, first I want to thank the reporter's report. Can you please turn to slide number 1? Okay, so here you mentioned the Reynolds number, so but I didn't see the apply of this number in the next few slides. So did you apply the Reynolds number into your experiment?
Because wind well is when the water stream velocity will decrease. So the one reason is because of viscosity. So we use the Reynolds number to say the viscosity can apply on our experiments.
Okay. Another question is that what is the limit of observing the phenomenon? For example, at what range of flow rate or pressure will this phenomenon happen?
You say
The limits or the range of some specific parameters.
The further the hydrodrome will occur when the Fowler number is less than 1, and when the data is a straight line.
Okay, that's the answer.
Okay, time is up. The opponent, you have 3 minutes to prepare your presentation. So, 它可以要 switch 吗？
它有亮没？它有亮。没有插吗？没有。等一下帮我重接一下。
把不要再接上去，你直接接上去。不会低。它怎么会关掉？
关掉了。
自己下档。
主要是热档比较少。隔壁杆也少。
真的。有。先等它出来，再开始算。它还没够亮可以开始吗？好 ，so please go ahead.
This is our position on program for unscheduled disk. This I will repeat the test again. A main disk with a hole at the center sinks in a container filled with water. When the vertical water jet hits the center of the disk, it may flow on the water surface. Explain the phenomenon and investigate the relevant parameters. So, in this case, I think the test will want us to study more like when the disk is originally under the water surface a little bit, and we put the vertical water jet on it, and what will it happen? And so basically this is the structure of how the reporter solving the problem. First, they introduce some hydraulic drums theory. Second, some functions and analytic findings, some experimental graphs, and what's the limits of the phenomenon. Okay, this is our pros and cons of the report. First, we use many theoretical models via literature. Second, simple, understandable qualitative explanation of observation. For example, some experiments related to some essential theories. Third, they use some media and graphs. Fourth, some functions to prove the points of the methods. However, they lack some explanation of how to apply the complicated functions and the unclear prediction of theoretical movements with reality. And I think some parameters are out of control, and some incomplete investigation of through circulation. Okay, and about the experiments, they have accurate and reproducible setup and clear investigation in graphs, comparison of velocity and diameter of the disk. But some parameters are not mentioned clearly enough, and the error bar are not shown. Basically, not all theory and experience are linked together, and no measurement of exact parameters and media applied. And we don't know if the theory ideal situation are experimentally verified. About the theory, some relevant modeling of hydraulic drum related to the experiment, some own modification of parameters that the opponent hopes to control, but however, unclear how modification of theory was actually done, and some models are not less sufficient, and no model of ideal experimental setup. This is the 3 points that we wanted discussion. The first one is the definition of the questions. The second is how to observe the height of the hydraulic drum. And the third is how we control different situations and parameters. And let's see all of the time, and I want to start the discussion. Okay. The first question I want to ask here is that if you only put the disk on the water, and with no water on the disk, will it float or will it sink?
If we just put the disk on the water surface, it will float on the water surface because the surface tension. But the problem statement clearly said that we have to sink the disk.
Yeah. So in your experiment, do you put the disk under the water and you use a water jet to hit it?
Yes.
Okay. second question would be, how do you control the water jet? Its diameter for the water jet?
You can see our experiment setup, and when put the nozzle very close to the disc, and the diameter of the water jet is the pipe, the pipe's diameter.
Okay. Then I think we have a question that I asked previously. What's the limit of the flow rate? Like about what range will this phenomenon happen? Yeah.
When we just consider the hydraulic drum,
Yeah.
and the Fowler number is larger than 1, and the hydraulic drum will occur. And so we can use the theory to calculate the lower limit of water speed for the hydraulic drum, and we find the velocity, and we put this on the situation of the velocity, and it can flow, and this is the limit. And this is the limit.
Okay. The next question is the diameter of the disc, the hole inside, the hole, and the diameter of the jet, is there a link between the two?
When the water jet size is larger than the hole size, it won't occur the hydraulic drum, and it can still flow, and it's because of vortex.
So you mean when the water jet's diameter is larger than the disc, then there is no hydraulic drum?
No, when the water jet size is larger than hole size, it will occur hydraulic drum.
So when it's smaller than the hole, then
It won't, yes.
okay. The next question is how do you observe the height of the hydraulic drum?
Yes.
How?
When put the cameras inside our container, and it's very obvious.
Okay. There are some parameters that we want to discuss. First, what kind of disc do you use? I saw it's the metal disc, right?
Yes, it's aluminum.
Okay. Have you tried using other discs?
We use, but yes, we use another, but when final choose aluminum disc.
Why?
Because the aluminum is lighter.
Oh, okay. So it can we can easily find this phenomena with using the aluminum disc.
Yes.
Okay. Okay. As for the density of the disc, aluminum, the density of aluminum is larger than the water, and so yes, in this experiment, how do you use your theory to match your model? Because you have real numbers, you have true numbers, but I think in your experiment they are not shown in your graphs or in parameters.
We show a flow number, and according to the flow number, we calculate our lower limits.
Okay.
And the random number to prove our water jet's velocity is laminar flow.
Okay. I saw in your video that there are some bubbles under the water surface. Yes. Will that influence the phenomena?
It will influence the phenomena,
How?
but
How? Yeah. Yeah.
And the bubble will float on the water, and it will force one to it
so do you discover how the force of the bubbles or the pressure influence the phenomenon?
But we know the plan about the water, but when we actually calculate the upward forces and the upward forces and we think the bubbles influence is very slow.
Okay, so you just
It's very
ignore
slow.
it. Right. Okay. Another question I want to ask here is that do you measure the pressure of the water in different places, positions?
And it's the pressure we can calculate and can really to measure. But we can from the burning slope know when the water velocity is from center to the edge. The flow rate is from light to the lower. And according to Bruno Foyle, the center is the large and the edge is lower.
Okay, you mentioned the Bernoulli equation in your report, but however, I think that the Bernoulli equation applies in a locked system. The pressure and the volume, we can apply that in a locked system, but in this case, I think the hydraulic drum and of course the watershed is an open system, but there. So do you think about that problem?
Can you speak again?
I mean, okay. But I think that the Bernoulli equation, we can apply it only when it's a locked system. For instance, a pipe and this.
And we can roughly use the Bernoulli law, and we will add a correction.
All right. Have you tried using this without holes? Using only discs, like you said, your aluminum disc without holes.
Yes, and it can fall when a water day hits the disc percent, and it can fall.
Then what's the difference between the one with no hole and the one with hole?
One has the vortex and one no vortex.
All right. Do you think the temperature of the water will affect the phenomena?
And because we don't consider the surface tension, so I think the temperature is not good.
Okay. Then, in your experiment, the vortex, the circulation, and the circulation of the water in the container is essential. So, do you think when the circulation touches the side of the container, will it affect the circulation?
I think the effect is very low because it will affect this is just the area, and the container is there, and so it is not influencing.
Okay. Can you please turn to page 10 in your report? Okay. So here, how is the shear stress here, and do you use this shear stress to explain your phenomena or your experiment?
Yes, we use the surface to explain, and this is one reason why the strength is low. It's one reason why the flow rate will decrease when spreading over the disc.
Okay, that's the end of my opponent. Thank you.
Okay. So So Paul, please summarize the discussion in 1 minute.
Okay. First, we discuss the definition of the problem and how we control the water jet. And the reporter said that we can observe the phenomenon both when there's a jet and with no jet, but without clear explanation. And second, for different situations and parameters. But for most of the parameters, for example, the bubbles, the reporter mostly ignored it, and for the link between the theory and the experiments, there are no clear link between the two. And for example, the Reynolds number and the shear stress. And for the hydraulic drum, for the height, I think it is.
Okay, time is up. So the reviewer, please ask questions to the reporter and the opponent. You have 3 minutes.
So the first question, the reporter, can you consider the pressure of water for the container when you measure the height?
Because the container is larger than this, and it has I think it won't affect the hydraulic drum's height.
Okay, got it, thank you. And what is the major parameter that causes the disk flow? What do you think is the major parameter that causes this flow?
I think it's hydrodynamic.
Okay, thank you. And to the opponent, what do you think is the major parameter that causes this flow?
First, I think that it is the you have the forces of the water jet. Yes, and gravity. So the anti-forces let buoyancy that the water gives the disk causes the inflow, and when we do it without the hole, then it's the surface tension, and the buoyancy.
Okay, thank you. And to the reporter, did you consider the surface tension in your model?
And because the problem statement is very clear, say sinks in the water, sinks underwater, so the surface tension won't happen.
Okay, thank you. And what is the lowest velocity of the water that the disk will float? What is the lowest velocity of the water that will make the disk float?
And we use different size disks, and so we will use the number to calculate what flow rate will make the disk float.
And how did you measure the velocity of the water?
We use the P over the AB, and we use a container to the water.
Okay, time is up. So review, you have 2 minutes to prepare the presentation. please take the floor. Okay, 4 minutes.
Hello everyone, I'm from Team Music, and this is my view of the unthinkable disk. And this is the problem statement. And this is the overview of the reporter's presentation. The theory is about Bernoulli principle and hydraulic shock. The cell is a metal disc with a hole in the middle, and vertical water jet through the hole. And the conclusion is hydraulic jump and the underwater fortress makes the disc unsinkable. And this is the strength and areas of improvement of the reporter. The strength is slow motion animation, and I have neat diagram. And they have a top view image and side view, and strong theory support. And their areas of improvement is they're set up on page 4 made with their PowerPoint isn't that clear. And too much of theory, but not enough supporting of evidence. Next, they have not enough explanation of the force diagram of their fortress. And they need more explanation, they try and should do more on fitting their theory. And about the opponent, they did a well job on pointing at experimental problem and consider main points to the experiment. And their areas of improvement is that they have spent too much time talking about the pros and cons. And they didn't have enough of forward discussion. And this, their discussion. First, the opponent makes the point that the dead thing will float on the surface. The reporter responses that it will float up. It will float. And the second point raised by the opponent is, what is the range for the phenomenon will happen? And the reporter responses that when the force is larger than it's F. And the third point raised by the opponent is how to observe hydraulic jump. And the reporter's response is they can observe it from the side of the camera. And the fourth point raised by the opponent is how the bubble under the surface will affect the experiment. And their response is it will float and affect, but it isn't that significant. And the fifth point raised by the opponent is Bernoulli principle only appears in a locked system. And the reported response is they did have a correction to fix the error because it isn't a locked system. And our question is, first, did you consider the refraction of the water that will affect the height? And the answer from the reporter is they don't think it will affect the hydraulic jump height. Okay, the next question is, what is the major parameter to cause the phenomenon? And the answer from the reporter is hydraulic jump and forging, and the opponent also. Sorry. Okay, the third question is, did you consider the surface tension? And the answer from the reporter is no, because the disc will sink under the water, so the surface tension isn't that important. And this is the missing point. First, we believe that the water jet is prior to the phenomenon because when the jet hits the disc, the resultant force will equals to 0, which makes the disc float. And on the missing point, they have a lack of explanation with the chart. And next, the demonstration starts from when the disc is floating, which shows a little difference to the problem statement. And maybe we should be more focused on the experiment and talk more about the limit of water floating velocity. And maybe the vertical water jet is prior.
Okay, time's up. So, reporter, you have 2 minutes for your concluding remarks.
And the first one, I think the hydraulic jump and the underwater vortex is unsinkable. And we use the Ford number to calculate the idle limit velocity like chemicals by the and the surface tension is no need to take into consideration due to the problem statements mentioned things. And the demonstration, when we start to do our experiments, I put this under the water and use the water jet to hit its center, and then it will float on the and it will fall on the water surface. And so I don't start and I don't put this on the water surface and start the experiments.
So, any question from the jury? Professor Lee, please.
I'd like to see whether the height of the container is relevant parameter or not in your experiment. The height of the container.
I think the height of a container it will affect because the water jet will hit the bottom of the water jet will hit the bottom of the container.
I don't think it's a relevant parameter because basically the forces that the ruler mentioned is mostly on the surface of the water. Yes.
I think it will affect. If we discover if the container is like very deep, then the jet will not, then it will not hit back. But if the container is not that deep, maybe the reflection of the water jet will push the disc.
So, any question? No more question? Okay, let's start for the scoring for the jury. So let's show the score for the reporter. Seven, 5, 4, 5, and 7. So let's show the score for the component. 7, 5, 6, 7, and 8. We should score for the review. 6, 5, 5, 5, and 7. So any comment from the jury? So since no comment from the jury, so we have the 5 closed here. We have 10 minutes break. So please come back in 10 minutes. Opponent, please change problem to the reporter.
Okay, so I want to challenge problem number 7, 3-sided dice.
Number 7.
We accept.
Okay. So each team, please write down the name of the presenter on the board. Okay. So, reporter, please take the floor.
Okay, so here's our report of the three-sided cylinder dice, and we are Team Tesla from Filipino Senior High School. Okay, so here's our outline. So we have introduction, primary theories, methods, experiments, calculations, possibilities, analysis, improvisations, and extensions. So here's the introduction of the three-sided dice. So you have to land a coin on its side, and it's often associated with the idea of a rare occurrence. So what should be the physical and geometrical characteristics of a cylinder dice so that it has the same probability to land on the side and one of its faces? So here's the primary theories of this. So we have two primary theories. Method 1, coin and sphere, which is considered as a 3D model. And the second method is coin and circle, so considered as a 2D model. And here's our first method, coin and sphere. So you have to think that the chance of the coin lands on its edge will be a third if the surface area of the shaded central band is a third of the surface area of the whole sphere. So look at this model over here. So as what I said, this is a 3D model. So we have to consider that the three-sided cylinder dice is considered in the ball. So if the band area SB equals 2 times pi times t times r, and we want that S of B equals 4 pi r squared over 3, so t equals 2r over 3. So you have to know that as a triangle. So h squared plus t squared equals 2r squared and equals 3t squared. So h equals 2 t. And here's the second method. So if the thing that a chance on the coin lands on its edge will be a third, if the two dashed arcs make up 1/3 of the whole circumference of the circle. So we consider this in a paper. So x equals 60 degrees, so h equals 2r times sine 60 degrees. So it equals r times root 3. And t equals 2r times cosine 60, so it's equals r. So h equals root 3t. And so here's our experiment preparations. So we have coins of all sizes. So we 3D print our coins, and the height of each coin is 1 centimeter. And we change the diameter of each coin, so it's 2 root 2 and root 3. And so in this case, the 2 root 2 dice will be considered as sort of thinner, and the root 3 will be considered as sort of thicker. And we have 10 of each these dices, and we 3D print them, as what I just said, and to accommodate all the coins. And throw 10 for each, and throw for 100 times, so you get 1,000 data for each of a flat, smooth table. So here's our experiment on how we design. So we make 3 faces of the coins in X's, O's, and slashes. And we chose the 3-sided coins 10 in a group for 100 times in order to get 1,000 data of each 2 root 2 and root 3. We simply count the numbers of X's, O's, and slashes and define them with the statistic presented to be clearly shown. We have to calculate the possibilities for approvals. So here's our experimental data of 2 root 2. So we have 398 X's and 4 O's and 132 slashes. So here clearly shown our expectations and probabilities of each side is 333, since we got 1,000 data, so 333.33. So I think this doesn't match our theory. So our experimental calculation for 2 root 2, so we can set up a binomial hypothesis, and first define our hypothesis, and the null hypothesis H0, which means that a coin is fair, so the probability of getting an H is P1 over 3. And the alternative hypothesis H1, so which means that the coin is not fair, and so the probability of getting an H is P1/3. We now proceed on the basis that H0 is true, and calculate the probability that if P equals 1/3, then what is the probability of what we have seen and anything more extreme? And in our experiment, we saw 132 over 1,000 ages for our thin 3-sided dice coin. So if we let the X be the number of ages, we can work on a probability of this and anything more extreme by considering Px smaller than 132. So now we have a range that is 2 root 2 and root 3. So we have to get the exact 3-sided cylinder dice. So now we have to push on the extreme sides. So what if we can get a possibility that's lesser than 132? Okay, so we have to use the binomial population, and the sum of binomial population is a binomial population. We need to consider that Px lower than 132 because Px equals 1, x equals 2, all the way to x equals 132. And where, for example, size n equals 1,000 and p of 1/3, we have Px equals x. The binomial distribution nx p of x, 1 minus p and n minus p. Okay, so we have to calculate all the x equals 1 and all the way to x equals 132. So it's not essential if we calculate all in the binomial distribution. So to avoid calculating both these probabilities, which will be extreme time consuming, we take normal approximation to the binomial distribution. So p x lower than 132 equals phi of 132 minus expectation of x over root v of x. And p of x and v of x are expectation and the variance under H0, which we consider is true. And phi represents the cumulative distribution function of the standard normal distribution with means 0, standard deviation 1. So you can calculate the expectation variance using the binomial distribution. The expectation of x equals n times p, and n is 1,000 times the possibility is 1/3. So 1,000 times 1/3 was 233.33. So vx equals n of p times 1 minus p. It equals 1,000 times 1/3 times 2/3 equals 222.22, which then gives us p lower than x. Px lower than 132 equals phi 132 minus 333.33 over root 222.22. So it equals a 7.237559 times 10 minus 42. So that's a really low possibility. And here's the experiment data of the root 3. So we have 315 x's and 275 o's and 410 slashes. So the same, we have to consider that what if we can get a possibility in numbers over 410, like larger. Okay, so experimental probability of root 3s. So similarly like the methods we did in 2 root 2. In our experiment with our 3-sided dice coin, so we solve 410 ages, so we could calculate Px more than 410. And it equals 1 minus Px lower than 410. So I have an equation that's 1 minus 5, 410 minus 333.33, and over root 222.22. So it gets the possibility of 1.350/446 times 10 minus 7. Again, it's a really low possibility in the binomial distribution. So what we're going to get is a range. So it's between 2 root 2 and root 3. And like obviously 2 root 2 and root 3 aren't the exact range we are going to find. And so we have further extensions, and in denial of the 2 primary examples, we speculate the exact height of the coins might be a number a. So number 1 to get a is between root 3 and 2 root 2. And similarly imitating 3D print the new variations of coins requiring a limit of t equals 1. So here we do the experiments of 7/3 and 2. So by doing the binomial distribution, we can consider that 2 over 2 and with the other most extreme of the three-sided dice. And in 7/3, we get 336 O's and 374 O's and 280 slashes. And h equals 2, we get 332 X's and 328 O's and 330 and 340 slashes. So I think clearly we can consider that the exact diameter of our dice is 2. Okay, so here's the end of our presentation, and thank you for your attention.
Okay. So, opponent, you can ask question to the reporter. 2 minutes.
So, okay, can you please turn to page 11? So, how did you get the equation?
You mean the binomial?
Yeah.
This equation means we use the binomial distribution. So consider x equals 1 all the way plus x equals 132. So we can get a possibility of x lower than 132.
Okay.
Yeah.
So, did you have any demonstration of how you throw the dice?
How we draw the dice?
Throw the dice, yeah.
Throw the dice.
Yeah.
That demonstration.
Yeah.
Sorry, but yeah, we didn't have that demonstration here.
Okay. So, as you said, you briefly throw the dice. So,
Yeah.
can you make sure the center is in the middle of the dice, or otherwise it won't be a fair dice?
So you mean we have to test the dice first, right?
Yeah.
Okay, so actually each dice we throw it for 100 times, and we have sure that the whole number is the same,
So
like the last number we got.
Can you make sure your dice is a fair dice?
Yes.
Okay. So, can you make sure you also print the flat side of your dice?
Flat side?
Yeah.
Yeah, of course.
Okay. So how do you do the experiment? How do you control your initial conditions, or how do you make sure you have every same time? You have every same condition in the same time.
Okay, so for general, like we close the doors and fans and like some of the lights, like beyond the lights, and so I have to sure that around the table, and we set up like a wall around the table, so we are sure that the coins won't bounce out. So in the case when we throw dice, we accommodate it all in all, so it's actually just random, and we throw the dice on the table and it hits the wall, and this calculated into the
Time is up. So opponent, you have 3 minutes for preparation. Okay, owner, please take the floor.
Should have 26.
Go ahead, please.
投上去哦。
So I'm the opponent of the three-sided dice, and I'm from composing. So here's the problem statement. The three-sided die to any coin on its side is often associated with the idea of a real occurrence, which is the physical and geometrical characteristics of the cylindrical dice or that has the same probability to lie on its sides in one of its face. So their main focus is on the coin and sphere, and another one is the 2D coin and circle. So here's how the reporters solve the problem. So first, their observation will be numbers of each side to land on the same probability. And the theory comes from the mathematical probability which they have given an equation. So the setup will be coins of different sizes and 3D printers in different sizes of the dice and a cup and a flat smooth table. And the data analyzes the statistics. And in conclusion, they made a conclusion in that if the height will be 2 centimeters, it's more close. It gets the closest probability to what the problem statement stated. So here's the pros and cons of the reporter's report. So the pros are provide different methods to solve the question, which they use 3D and 2D models to solve the problem. And here's the cons. They have poor time management, and they didn't really mention physical characteristics of the cylindrical dice, and the lack of explaining mathematical equation. So here's the discussion which I want to talk about with the reporter afterwards. So first, under what condition are the so-called probability obtained? And what kind of known condition can be called random? Well, the determinant of the odds of each side of the dice. So yeah, and how do you make sure the side of the dice is flat? And is your 3D model have even mass? Can you prove it? And last, can your data beat your theory? So now I'm going to go on the discussion. So first, can you explain more about how do you make, what is the 2D model you stage in your PowerPoint?
You mean how do I print it, or how do I make sure it's?
How do you define as a 2D model?
How do I define as a 3D model?
2D model.
Oh, yeah. Okay, so. Okay, so like, we did this all on the paper, so we have to consider that the 3 spheres are the same, right?
So actually, that won't be a 2D model. So you calculate it in 2D models, like you just.
Yeah. X.
Okay. So you see only one of those sides.
No. Like we calculate the degrees and the sides.
Okay.
Like from the 2D side.
Okay.
Yeah.
Okay. Have you ever thought about the rebounds when you fall down?
Fall down to the.
Fall down to the ground or table.
then we denied the experiment.
So you didn't do that in your experiment?
We haven't that, but like we take the data off. Because like when it flows down to the floor, then its conditions are different from those on the table, right?
Okay. So you said that you make sure your initial condition is like the same every time?
What do you mean initial condition?
So like how you throw the dice?
Yeah, I accommodate all the dice in the cup. Like
So-
I didn't care about how they are in the cup, so I considered that as a ring.
So the angles and there are like random.
Exactly different every time.
Okay, so do you have any height of your cup and your table?
Height?
Yeah. How the height where you throw the dice? Or you just like throw it randomly? Is there any height, like you throw it from 10 centimeters of the table?
I didn't really do the parameters of the height. And because all the conditions of the dice in the cup are random, and so I don't think that really matters.
Okay, you don't think it will matter. So, do you think? So, why did you choose 703 and 2? Like, there's a lot more numbers between 2 times root 2 and 3 root 3. So, why did you choose 2 and 7/3?
Let's just see. Like I think it'll be right. And 2 and 7/3, like they're actually in, like it's actually in about the same place between root 3 and root 2. Like the distance between 7/3 and root 2, and 7/3 and 2.
So you actually just choose it because there's a.
Because like I think it divides the area into 4.
Oh, okay, got it. So do your data fit your theory?
Yes.
Okay. Can you go to your data page?
Data page. Which one do you want? Root 2 or root 3?
The second one.
This one?
Yeah. So
here there's 100 times, and we drew 10 for each.
So can you prove how your data fit your theory?
You mean like the front model part?
Yeah.
Like how these will fit in others?
Yeah.
So actually we separated into a 3D model which we consider the sphere, and this is about the central angle part. Okay, so at first we think those two models, like these two models will like be accurate, but we cannot be sure of which one's right. So through it's like in reality, like it proves that both of them are wrong. So that means that both of them are just huge, like in theory parts.
Yes. So can you explain more about your physical characteristic of the dice, because I didn't really see your physical characteristics.
What kind of physical?
So maybe did you have any like ratios, or have you ever thought about how the center of the dice and your mass?
I didn't thought of the mass because like I threw it into a 3D printer.
Yeah.
So like all the materials it use, like each dice is the same. Like I can control that. So I don't have to.
You have different ratio, right? You have a one.
So like for each 2 size dices and each root 3 dices, I can control that each of the materials that I fill up are the same. So I don't have to like get it from mass again because I can control it from the printer.
So
like,
you make sure your 3D printer has the same mass every time.
Yeah.
Yeah. Okay.
And for the ratio part, like 2 root 2, like the height is all calculated in 1 centimeter. So the diameter is 2 root 2 centimeters, and the other diameter is 3 centimeters. So I believe that's a ratio for it.
Okay. So have you ever thought about when it falls down, will there will be any energy decay? So yeah. So can you explain? So what do you think the energy can affect your results?
I think the reason why I don't really consider about energy because like we are talking about the possibility.
Yeah.
So like our experiment we counted when it throws on the table, like when it totally doesn't move there. So I don't have to care about the energy decay because we are counting about like the slashes and X's and O's we've got, right? So I'm doing the statistics about the ranges I got instead of analyzing the energy part. And so if we analyze the energy part, then we'll have to conclude about the first
So because in our own experiment we found that if you need to like lit up the die, you need a lot more energy than letting it down. So will that affect your result because you didn't actually count in the energy inside your experiment?
Yeah, so we do that in the random start. So
Okay.
we can include it in the result.
Okay. And then, so is there any strange result in your data? So like when it falls down to the ground, it has a strange ratio of how many times it landed on its face and landing on its sides. Like maybe you have a dicycle from the side a lot more times than landing on its face. Is there any strange data? Or
Yeah.
is like even?
Yeah, there are, but like what I just told you, we count about the last time. So if you flip too much times and until it flows onto the floor, then don't calculate that one. Like that piece of experiment.
Okay.
Yeah.
So, and can you turn to page 9? So, okay.
Yes.
So, do you have any maximum or minimum a value of your dice?
What value?
Like ratio or something like that? Because you only, according to your theory, you only got the ratio of 1 to root 2 times 2 times root 2 and root 3. Do you think is there any possibility that the value or the range of the value will get bigger? Like maybe there's a value of 3 times root 2.
Oh, you mean if I change this the one part? And I believe that you mean like 2, 3, right? So if 101, then it would be like 1 and 3 over 2, right?
Yeah.
Yeah, so that's actually considered in our exact range of the three-sided cylinder dice, right? So what we get for root 2 and root 3 is just for extreme parts. So like from the extreme parts, we can narrow it down and get the exact range.
Okay.
Yeah. So I think that's included in between that one and root 2.
Okay. So nice. And can you just like simply depict the energy transfer of the dice? Like because although you say that energy won't really affect, but we think that energy might affect the dice of the possibility of landing on its face and on its sides. So can you like just briefly explain?
Okay, but I have to clear that I think energy will like affect.
Yeah.
But we don't take like our experiment doesn't include the energy
Yeah.
part.
So
Okay,
that
so
is
like
one of
briefly
the
this.
parameters.
Okay, so in my thinking, so when the dice got to the surface of the table, like when it's on the side, then it has a probability for getting two sides. So this includes the central mass part of the dice, so it can rather go on to the slash part or the O part than what I just think. Yeah, so there are two different sides.
So since you use the ratio, have you ever thought about using different angles?
Different angles.
Yeah, so
What angles?
like solid angles.
Solid angles.
Yeah.
What do you mean solid angles?
Okay, never mind.
Okay.
So, do you have any geometrical explanation of your dice?
Geometrical explanation?
Yeah.
Yeah, I believe
So-
it's in two parts.
So how do you prove that? If you look from the side, it will be a kind of different explanation from looking from the space.
What do you mean?
So how about you? Because you see the dice from the space, right?
This one, yes, because it's a 2D model, and this is actually a 3D model. So like the dice is concluded in a ball. So like the surface of the ball, we consider it to be 1/3 of each size of the dice, right?
Okay.
Like the front part and the back part and the side part. So we divide the sphere of the ball into 3 parts and matches in all 3. So I believe that's not a problem.
So why do you decide to use the 2D model to phrase your ratio?
like we just want to be more comprehensive and more fundamental. Like for 3D, we have to have 2D. And like I've got over many articles, and they all use 2D. So that the extra part is that we analyze a 3D motion.
So did you consider your top face and bottom face as the same face or different face?
Top face and back face, yeah.
Yeah. So
It's
you
the
consider
same
as the same one?
Yeah, of course.
So if you bend it in like not enough height, it will just fall down, but instead of turning in, so
Sorry, okay, time is up.
Thank you.
So Hunan, please summarize the discussion.
So we talked about why did he use 2D model and 3D model, how did he phrase it. So he used 2D model to be more comprehensive and more fundamental to phrase and get a ratio of their height and their scalar radius. And then we talked about why did he use the 7/C and 2 as their ratio, because it can be separated into four equal parts of their 2 times root 2 and root 3. And their physical characteristic has the same mass because they use 3D printer to print it with a filled size. And then they didn't actually do results because they consider it as the randomized folding possibility, and they didn't actually use energy because they think they will affect, but it might not be effective.
So review and expression to the reporter at home in 3 minutes.
And my first question is how to define the random situation. I'm sorry, after content.
Okay, so how do I define it in my experimental setup? So like all 10 dices will throw in a pair. Like it's a
So we decided to throw it randomly, just like in random height and random angle. Yeah.
Okay. And my second question is, does the releasing height affect the result?
Releasing height?
Yeah.
Because what we only get is a possibility of 1/3 of each. So I think the height doesn't.
Your answer is no.
Okay.
We think it will affect because when it didn't have the enough height, it will just fall down from your hands or from your.
Oh, yes, I understand. And my third question is, did you think the softness of the floor would affect the result?
Softness?
Softness, the material of the floor.
Yeah, but we actually we throw it on the table.
Oh, okay. Yes. For your opinion?
So we think it might affect because the different size of the table have the different friction, and it might affect
Yes,
the.
okay, thank you. And my third question is, does the density of the dice would affect the results?
Okay, so for 202 and we have the same mass and the same volume. So I think we didn't do anything about the density. Yeah.
Okay, and for your opinion?
So we think that mass may affect, but it won't really affect without different radius or different ratio of your dice.
So, yes.
So I think it might affect.
My first question, did you think the air resistance would affect the result?
Air?
Yeah, air resistance.
Air resistance. I think we controlled it well. Like if the air resistance isn't controlled, then I will consider it as a random use.
In every condition,
In
in every situation.
Yeah, I controlled this situation in my experience. And like if in reality, so the situation always changes, right? So it considers as a random use.
For that, did you think
We think the air resistance will affect because the air resistance will affect the energy when it falls down. So if the air resistance is big enough, it will.
Yes, understand. Thank you. And my next question is there something else needed to take into account except the ratio of the height and the rate and the thickness of the dice?
Okay, so I think the most important thing in what I've done is test all the dices after it's
Anything else needed to take into account?
and like the surface of the table and use.
Okay, time is up. So you have 2 minutes for the preparation. You present. Okay, time is up. So review, please take the floor. You have 4 minutes.
Greetings everyone, I'm reviewer Xu For the television, I'm going to review problem number 7, three-sided dice. As a problem statement said, we should investigate the physical and geometrical characteristics of a cylindrical dice so that it has the same probability to land on its side and one of its faces. And I think we should manifest on what the dimension of a three-sided dice. And as our review of Thornton, in his theory, he used two-dimension model and three-dimension model and some mathematical calculation, and that is only statistics foundation. And in their experiment, they just use different sides of the coins. And their advantage is they have many theoretical calculation. And but we will have some suggestion. I think his lack of the parameters connected and lack of actual situation and lack of observation and lack of the experimental data to compare with the theoretical data. And our other opponent, he disguised the under that conditions are the so-called probability of team, and my suggestion is he has focused on the something like the unjust. So come to the discussion. I asked how to define the random condition. Gordon reported his answer. He just used the card to draw the dice. And for your opinion, he thinks the random condition should based on the random angle and height. And in my opinion, I think I agree with the opponent. But then if the height is too small, the dice will directly hit the table, so it won't rotate and to gas to release the real occurrence. And what if the releasing height effect are reported on opponent state? No, but I think the releasing height would affect just like the previously seen. And the releasing height the releasing height is related to the potential energy of the dice, and thus it has the more kinetic energy to rebound and more material. And I think actually if the material and content of the contact surface will affect, and reporter just do his experiment on the table, and the opponent say yes. And I think the material of this surface will related to the coefficient of restitution of the dice. So I think it will affect the result. He'll simply describe the energy transformation of the motion of the dice as for the opponent, and I think the transformation, energy transformation is.
Sorry,
Thank you.
So reporter, please present your concluding remarks. You have 2 minutes.
Okay, so I have to sincerely thank for the opponent and the reviewer for questioning my topic. And I have to remark that the opponent talked about the energy, but it's the shape that really affects it. So I think it's an understanding of how we did our experiments. And like the initial state, about the relevance of the initial state. And I think it's because of a different way we did our experiments, so like the questions aren't really accurate. And like I think like instead of analyzing the energy, so what I've done to this experiment is that we calculated only about the results, and I think the dice, the value of the dice is about 333, like over the affected parts, so to get the right possibility. Okay, then I think that's my remark.
Okay, thank you. So, any question from jury?
Well, could you please show me your experimental data? I remember something.
Okay, this work.
The whole set of dice. The table.
Okay.
Okay. Yeah, this one. Okay. The cross and the O means the top and the down surface.
Yeah.
So I wonder why those two data are so different.
I think that's the uncontrollable parameters when we're doing the exact experiment in reality.
It should be the same.
Yeah,
I see.
That's what like we wrote the thing out and like it's unpredicted.
And then you think this?
So in my opinion, the height might affect how it will fall down, because when the height is not enough, you like when you throw it like almost no degrees, like 0 degrees, you only fall down from only one side, so you only fall on this face instead of turning to the other face.
I think by the result and the experience done by the party, it isn't really occurs in a rare occurrence.
I think I have an explanation. Like we make the randomness like inside the cup. So I think the meaning of a difference between 398 X's and 470 O's. Like it's just because there's a really low percentage of landing on the slash board. Just because like the 100 minus 132, it's more divided to the O part because it's random inside the cup. So I think there's more like angles or something that leads it to the other side.
Okay. Before your dice just at rest and your dice really bouncing around.
Yeah. like it bounces around the table.
That's the opponent and the reviewer just keep asking if the height matters.
Yeah.
Okay, you just reply no. Actually, you got to have enough height. So the dice just bouncing around and before it just get rest, right?
Yes.
So that will be the resonance.
Oh, yeah.
Okay. Because you did not show the video, we really cannot tell how you did the firm.
Yeah, but I did consider and make sure that the dice were right. Like it isn't too low.
Okay. That is what I want to know.
So, no further question? So, when we go on the type of scoring. It's okay for the scoring. Okay, let's show the score for the reporter. 6, 5, 6, 8, and 8. Let's show the score for the opponent. 7, 5, 6, 6, and 6. And let's show the score for the review. 7, 5, 6, 5, and 6. So any comment on the jury? So there's no comments. The 5 of this session is closed here. Let's give everyone here a big hand.